About dimensional analysis. Dimensional analysis is the main way, not the main way, because there are multiple ways we solve problems, but this is one of the most common. Like more than 90% of the problems are solved using dimensional analysis. We'll talk about some other ways of solving problems. Now, when we do dimensional analysis, like for example the problem we were doing yesterday, 100 picometers. This is our given, and our given is going to have some dimension, which is called the unit here, and there's going to be a certain number of sig figs, which gives us an idea of the precision of it, and then certainty. And so this one is a little bit ambiguous because when we have zeros after the first non-zero, then it could be taken as one sig fig. Like one sig fig is, let's say you're counting people at the park, and you say, there's about 100 people at the park. That could be anywhere from, let's say, 50 to 149 people. Or it could be more precise, like 2 or 3, or infinite sig fig. Maybe there are 100 people at the park, so that would be a case where you can't have half a person. So. But anyway, then we tack on these things. These things are called conversion factors, and they're just relationships. And conversion factors. And so what we try to do here is we try to relate picometers to something else. So for example, if we related picometers to meters, then there are 10 to the minus 12 meters per picometer. But normally when I have 10 to the minus 12 here, to make it easier to input in the calculator, I'll just do 1 times, But you think 1 times anything, it's just itself. So is that really necessary? But if you don't, sometimes you're off by a factor of 10 in the calculator. So it's good just to go ahead and do that. But here, 1 times 10 to the minus 12 meters is 1 picometer, or 1 trillion picometers in a meter. Did I already write those down? No? Did we go through this?
Sort of.
All right. Yeah, there are different ways of writing this, or we could say that there's point O. Okay, how many zeros? I need 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros in a 1 meters is equivalent to 1 picometer. So 1 picometer is this many meters. Or I could invert it, at least the numerical part of it, and put it down here. And that is 1 meter is equivalent to 1, okay, this would be a trillion. So 1, 2, 3, 1, 2, 3, picometers. And so there are 1 trillion picometers in a meter. All these say the same because they're all the same ratio. And what a conversion factor is just some ratio, relates to or more things like that. Now with a conversion factor, we always have to think in terms of sig figs. So for example, if we had 3 sig figs here, then I want at least 3 sig figs in my conversion factor. The minimum would be 3. Ideally, like 4 or 5. Did I talk about this? Probably not. Normally we want to minimize the round off error, and so in our conversion factors, if we have a choice, sometimes we don't have a choice, but if we have a choice, we want to use more, at least 1 more than the given. And so if the given has 3, I'd like to use 4 in my conversion factor here. That's ideal. But in this case, I don't have to worry because this conversion factor is special. This conversion factor has how many sig figs? 1? 1 sig fig? Now, 1 sig fig is not correct, actually. It's not correct because if it's 1 sig fig, then you're saying, there's about, we'll go here. There's roughly a trillion, anywhere from 500 million to 1.4 trillion picometers in a meter. Does that sound about right? Anywhere from maybe 500 million to 1.4 trillion picometers. Because if it were 1 sig fig, that's what you'd be talking about, because you'd have that level of precision. With 1 sig fig, the level of precision is not so great. Is that what we're talking about for this? No. What we're talking about for this is called an exact. This is by definition. Anything by definition is exact, and they're exactly 1 trillion picometers in a meter, which means how many sig figs? Infinite sig figs. Right? And so this is infinite sig figs, so we don't really have to worry. There's plenty of sig figs here. Then we go on to something like this. We might go on to 100 centimeters per meter. So what we're looking at are the dimensions. Picometers canceling, meters canceling. This gives us centimeters. How many sig figs here? Is this a bit ambiguous? Maybe that's 1 sig fig, maybe it's 2, maybe it's 3 sig figs, or maybe it's infinite sig figs. Is it ambiguous in that way? How many sig figs in this? So if I said there's 1 sig fig, then this is the way I'd read it. If that were 1 sig fig, then there are, approximately 100 centimeters in a meter, plus or minus 50. So it'd be anywhere from 50 to 150 centimeters in a meter. Does that sound about the right level of precision? The right level of uncertainty? That would be 1 sig fig. If you went to 3, let's call it 3 sig figs. If we called this 3 sig figs, then with 3 sig figs, thered be anywhere from 99.5, which would round to 100, up to 100.4, which would also round to 100. And so it'd be between 99.5 and 100.4 centimeters in a meter. Does that make sense that it's 3 sig figs? Yeah? Yes?
So if you don't specify on a question how many sig figs you'd like us to work with, we just look at the given to determine how many we should use that word.
Yeah, but the given, this given is a little bit ambiguous, because it can mean different things. 100 can mean different things, right? Just like this. This 100 can mean different things. What does this 100 mean? We have a choice. 1 sig fig, 2 sig fig, 3 sig figs, or infinite sig figs. What would be your choice? Yeah, this is by definition. There's exactly 100 centimeters per meter, right? Exactly. And so that's by definition. So this is infinite sig figs, whereas this 100 we still don't know. Now, if I'm talking about the diameter of a hydrogen atom, then it's likely it's not exact. Yeah, that's for sure. Not exact. But if we're talking about 100 like this, then this is exact. So this is infinite sig figs, this is infinite sig figs. And then I need to go to inches, right? And I know there's a relationship. There's 2.54 centimeters. So the centimeters cancel out, and that takes me to inches. How many sig figs here in this one? 3 or infinite? Yeah, this is going to be infinite. Why? Because you memorized this is by definition. This is the only odd one that's by definition. All these other ones are, like how many quarts are in a gallon? Is it 1 sig fig, like 4 quarts, anywhere from 3.5 to 4.4 quarts in a gallon? Or is it exactly 4 quarts in a gallon? It's exactly 4 quarts in a gallon, so there's infinite number of sig figs. If we're doing 4 quarts to a gallon, infinite sig figs. And so these are the types of things. So this is infinite sig figs, infinite sig figs, infinite sig figs. And therefore, our answer is going to be limited by how many sig figs we have over here. And so we like to say, okay, we're going to assume there are 3 sig figs here. If we assume there are 3 sig figs, then what is the size of this? Did I already punch out the answer for this? No? Okay, let's do that one now. Oops. Turn on the computer to do that. Oh. punch along with me and see if we get the same answer. That would be great. You know, we do it as a check. You're checking me, you know, because I could miskey it, or I'm going to check you. In science, you know how answers are determined in science? You know, if you got the correct answer or not? When you start working in science, there's no answer book for everything. You know, for every single question in the universe, there's no answer book for that. And so the way people check their answers is not by looking it up or not by asking somebody, because, you know, pretty soon you might be the only person working in that particular field. You know, and you're the expert in that particular field. There might not be anybody to consult for the correct answer. And so pretty soon you can't rely on somebody else. And instead you rely on your peers. So science is checked by peer review. You know, you check my answers, I check your answers. See, make sure we did it correctly. It's always a good thing to do because everybody's prone to errors. But anyway, I'm going to go here and we're going to do 100. Okay, the units first. We always work out the units first. So the units work out to inches, that's what we want. Then we do the numbers second. And so doing the numbers second, I start off with 100 times. Now this is why I need the 1, because the calculator, the way we enter scientific notation, if there's no 1 there, it's going to be off by a factor of 10. And so I go 1, and then I'm going to hit the double E key or the EXP key or the times 10 key. It's not the 10 to the whatever, but this is going to be 1 times 10 to the minus 12. And so some calculators want the number first, some calculators want the negative first. So that's 100 times 1 times 10 to the negative 12 times 100 divided by 2.54. So I get, well, let's say that's 3 sig figs. If there's 3 sig figs, then I want to write 4 sig figs in my answer because I need to show what digit was dropped. You can't leave that a mystery. You have to tell me what digit was dropped. So I'm going to carry 4 here, like this. And so some people wrote about 3.937, almost 4 inches. So does that sound about right? A hydrogen atom is about close to 4 inches in diameter. Does that sound about right? About 4 inches?
Yeah.
No, because a picometer, how big is a picometer? If we take a meter stick, we'd have to divide it into a trillion pieces. And one of those pieces would be a picometer in thickness, which means we need about 100 of those, but you could barely see it, right? Probably you can't see it. In fact, you can't see it, it's so small. And so a hydrogen atom is on the order of 100 picometers, which is so small to see, but 4 inches is no problem to see. And so it's not 4 inches because I'm missing something. What am I missing? It's 3.937 times 10 to the negative 9 inches. In other words, if that's 10 to the negative 9, I need 8 zeros. 1, 2, after the decimal, 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and then a 3.937 inches. That's how big it is in inches.
So would you rather us, when it comes to things like that, not put it in scientific notation at the end, and then just put the exact number for what this is translated into?
Well, you know, it's a matter of preference and what you're trying to show. You know, sometimes you're trying to show these big numbers, but so pretty soon we get to very, very big numbers and very, very small numbers. It becomes a hassle to do it in regular decimal forms. It's much easier to write it in scientific notation. But when it's written in scientific notation, we lose track of the magnitude, the size of it. And so a lot of people, when they do calculations like this, all they care about is, did they get a number in their calculator they can write on a piece of paper? They don't really think about the number. And so some people might end up answering that it's actually 4 inches in diameter. Well, how can a hydrogen atom be 4 inches in diameter? And so sometimes we got to think about what the numbers mean. And sometimes when we write it in scientific notation, we lose that perspective here. But this is too many sig figs. We need to round it to 3 sig figs, let's say. If we round it to 3 sig figs, then we're going to drop the 7. If we drop the 7, then we go 3.94 times 10 to the minus 9 inches. If we do it to 2 sig figs, it would be 3.9. If we do it to 1 sig fig, what would it round to 1 sig fig? 4. And so it depends on how many sig figs. Since this is a little bit ambiguous, we'll just call it 3 sig figs. All right. So sometimes we have a choice of, in the conversion factors, we just string along conversion factors, one after the other. And sometimes you don't know, where exactly you're going, and this is why I use that jungle path analogy. That is, sometimes this problem solving, dimensional analysis problem solving, is trying to pick your path through a jungle. You don't know which path to take. But, it's not a problem, because if you're faced, the problem is this. Sometimes when people are trying to find their way through the jungle, they won't pick any path. They'll just stay put. I see that happen on tests all the time, because I look at a dimensional analysis problem and it's blank. They didn't write anything because they couldn't even start down a path. What you want to do is you just want to start down some path, and if it dead ends, it's no big deal. If it dead ends, you just backtrack and go down a different path. Eventually you'll get it. That's the great thing about dimensional analysis. As long as you have all the paths open, you will get it if you have enough time. Is you just got to string them together. It's like connecting the puzzle pieces. All the puzzle pieces are there. You just have to string them together in the right order. And so that's the great thing about dimensional analysis. You don't need a plan. You don't need anything. You just try. It's just trial and error. You keep trying until you get it. But the thing is the important thing is to try, and not to freeze when confronted with this type of situation. And so let's take a look at some more dimensional analysis type problems.
So what would you say would be the best things to memorize for conversion?
Conversion factors?
Just give us the exact
The exact ones. Exact ones is exactly what I want you to know, because the other ones can be memorized a different number of digits. But it's a little bit more than that, because there are some that are useful, and so we just got to pick a number of digits to use for it. We haven't gotten there yet. Acceleration due to gravity? No, don't bother memorizing that. Speed of light? Don't bother. But the gas constant, we need to memorize that. We need to memorize it to how many sig figs? 4. If you're like me and it takes you time to memorize things, you get a head start, you get an early start. We haven't talked about gases yet. It's coming in the next chapter. Electron charge? No. None of these others we need, except this one, Avogadro's number. This Avogadro's constant here, which is given the symbol n sub a, we need to memorize that. How many sig figs? Because we can memorize a lot of sig figs. There's a huge number. I mean, this is rounded, but these digits keep going on and on. But how many would you guess we're going to memorize it to? How many sig figs would you guess? 4. Awesome. And so people memorize this to 6.022 times 10 to the 23rd. 10 to the 23rd is a huge number. Huge number.
What is that? All I know is 2 trillions. What is that? I know up to trillion.
You know up to trillion, so what is that? What is that is, there's special words for big numbers like that, which you could use, but you don't have to. Well, what we often do is we do this, we do it in terms of what we know. And so if you do 10 to the 23rd, Well, 10 to the 23rd would be like, what's the biggest, you know? You said you know trillion, so it's 10 to the 12th, right? And so that would be, could we do a trillion? Would that work? Trillion. No, trillion would give us 10 to the 20, 10 to the 24. That's not going to work. And so what we could do is this. We could do a billion trillion. Would that work? Yeah, billion trillion, that would take us to 10 to the 21. And so this is the way we could do it. We would do this. 6022. We move it 23 over. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So we got our 23 spaces out from here. And so we go like this: 1,000, million, billion, trillion. So I stop here at a trillion. And then go 1,000, million, billion. And so I'll stop here at a billion. And so at this point we have a billion. From this point down we have a trillion. And so we call this 602 billion trillion. That way we don't have to memorize there's special names for this, but we don't have to memorize the special names because in math, a 602 billion trillion is the same as whatever special name we have for that. And whatever special name we have for that is so rarely used that you're much more likely to remember billion trillion than that, okay? And so 602, I know I asked, how long would it take to count to a trillion? Did I ask that? No. How long would it take somebody to count from 1 to 602 billion trillion?
More than you have.
More years than you can live. So that's a huge number, right? So sometimes we lose sight, Did I ever tell you the density of gold? Did I tell you that? The density of gold is?
Mentioned gold, but I don't think you mentioned it's this is around like 20 grams.
Yeah, around 20 grams cubic centimeter. Sometimes people lose sight of the numbers. And so sometimes people do a calculation and they'll calculate the density of water. The density of water is 420 grams per cubic centimeter. If it's 420 grams per cubic centimeter, that makes it what? That makes it 20 times more dense than gold. Does that make any sense, number-wise? No. And so what we do is we think about the numbers. Do the numbers make sense? As a check, because sometimes there's no answer book to look at, and so we start thinking, do the numbers seem to make sense or not? Well, this is an enormous number and represents something that we don't have to worry about. Now, there are different paths to, actually not this one. Yeah, there are. I might have thought, hey, what, this is a waste of time. I could have done this faster, I didn't know because, you're just picking a path through the jungle, right? But somebody else might have picked some other path and said, oh, I got a faster way of doing this, right? And the faster way of doing this is like this. Rather than following this path that I took, they went this way. They went to meters, and then they said, well, rather than going this way, I'm going to go along a different path. In other words, I'm going to get rid of meters and then use this, because this takes me straight from meters and inches. So it's 39.37007874 inches. And so 1 meter is equivalent to 39. Now, how many sig figs should I use here? Because I can use a lot. I can use 4, 8. I can use 10 sig figs. With 10 sig figs in that number, should I use all 10? No, it's not necessary. The guideline is to use at least 1 more than you're given. And so let's say our given is 3, then we should use 4 sig figs here. And so I'm just going to go 39.37 inches in 1 meter. And I go, yes, this is a better path. Which path is better? Should we take the upper path here or the lower path to get to inches? Which one do you think is better?
The first one?
The upper path?
More exact.
Yeah, that's correct. I would have picked the upper path. Even though the lower path is shorter, the upper path is better. Does everybody see it? Why is the upper path better? Why is it more exact? Yeah. It's because the definition. These are all infinite sig figs. This one is approximate. We did rounding here. Therefore, we're introducing rounding error. And so there's round off error. What happened to all these other digits? All these other digits we dropped and ignored. You know? Which may be good, may be bad. Well, it depends on what side of the equation you are, but it's always an error. So when we round, we're going to introduce error there, unless they're all zeros, of course. But when we round, we introduce error. Whereas, did we have to round any of these? No, so we aren't introducing error. So I prefer, well, some of you prefer the upper path. Sometimes the error that's introduced is marginal. I mean, marginal to the extent that we call it negligible error. This is why we have the guideline. Let's talk about the error. We're doing one extra digit than our given. If we do one extra digit than our given, then we typically have minimal error we're introducing. And so let's take a look at this calculation with one extra than the given. And so I'm going to go 100 times 1 double E or EXP negative 12. Let me see if it takes negative first. No, it doesn't. This one I have to punch in the number and then the negative. Okay, times 39.37. 39.37 equals this. I get, do you see that? 3.937 times 10 to the minus 9 inches. Now, did that? Yes, you're right. The upper path is better because we'll see less error. But we aren't going to see the error until we get many digits out from here. And we got to round this to 3 digits anyway, right? And so, in this case, it serves as a pretty good guideline that the one extra is good at minimizing round-off error. But if we carry one extra, what about carrying 2 extra? Will we get a better answer if we carry 2 extra? The answer is yes. We will get a better answer if we carry 2 extra. But anyway, what was this is 3.937,000 times 10 to the minus 9 on the lower path. On the upper path is going to be a more accurate answer. Let's see, on the upper path, let's just redo it again since I didn't write the number down. Times 1 times 10 to the negative 12 divided by 2.54. Do you see? This is a more accurate answer because I didn't do that round off. By doing that round off, I lost all these digits here. Now it's important if you're allowed those digits because you're super high precision. If you're super high precision and you're allowed this, then we better use more digits, right? To make sure we don't lose those. But anyway, since we only have 3 sig figs here, we're going to end up with the same answer, 3.94. So it didn't really make a difference. And so the guideline is 1 extra is the minimum required. Now let's say we said, okay, you know what? I don't want to go 1 extra. I'm just going to go the same. So I'm given 3 sig figs. I'm going to use 3 sig figs here. And so let's see what happens there. So I'm going to go 100 times 1 times 10 to the minus 12. Okay, now instead of using 39.37, I'm going to use 3 sig figs here. If I use 3 sig figs, what would it be? 39.4. 39.4. Now look, rather than getting, what? I'd still end up with the same answer, but it could have easily gone the opposite way in this sense. So, but you can see I'm getting farther off than what I was before, because it was 3.937, now it's 3.94. Okay, now let's go to, rather than using 3 sig figs here, which is going to introduce more round off error, I'm going to go to 2 sig figs. 2 sig figs would be 100, let's go, times 1 times 10 to the negative 12. Okay, what would this be to 2 sig figs? It would be 39, sorry. Now I get 3.9 times 10 to the minus 9. Do you see increasing? Now, the opposite is true. If I go more, I'm better, but if I go 5 sig figs here, and I only have 3 sig figs in my given, then it's not going to make any difference. You know, 4 makes a big difference, but 5 makes very little difference over 4. And so even if you have 8 sig figs I could write here, or 10 sig figs I could write here, I would never write them all out, because pretty soon it's not even beneficial. Ooh, I didn't want to close this one. Let's leave that open. All right, now let's take a look. I don't have our textbook online, so I'm just going to show this. This is a Chem 1A textbook. And so in Chem 1A, this is chapter 1. For us, this is chapter 3. Let's use some dimensional analysis. We're going to do a trickier one. This is tougher. Sometimes we have these composite dimensions. These composite dimensions would be like this in problem number 75. In the United States, the volume of irrigation water is usually expressed in acre feet. This is a composite. This is volume. And so acre is area of land. So if you have area times height, that's equal to volume. So this is area times height, which is volume. But area is not in square feet. Area here is in acres. Okay, an acre of land is, I think this building here occupied about an acre of land. 1 acre or less. 1 acre foot is a volume of water sufficient to cover 1 acre of land to a depth of 1 foot. So if I had an acre foot of water, think of or visualize an acre of land being submerged in a foot of water, and that's the amount of water we have. They give us some, these are what I call conversion factors, or they give us some relationships. You know, conversion factors are just ratios, or they relate to things. There are 640 acres in a square mile. What do you think, exact or approximate? Well, let's think about that. In 1 mile, there's 5,280 feet. What do you think, exact or approximate? In other words, by definition or approximately? Okay, this is by definition. By definition, there's 5,280 feet in a mile. Exactly. Now let's go back to this one. What do you think? Approximately 640? Plus or minus half an acre or something? Or do you think this is by definition? This is by definition. Yeah. This is exact. There's exactly 648 acres in a square mile. And there's exactly 5,280 feet in a mile. Okay, this one you don't have to memorize, but this one you should have memorized. The principal lake in the California Water Project is Lake Oroville. Its water storage capacity is listed as 3.54 times 10 to the 6 acre feet. 3.54 times 10 to the 6. You know, what's another way of saying that? 10 to the 6 is how many? 10 to the 6 we call a million. And so another way of saying this is the 3.54 million acre feet of water in Lake Oroville. Well, that's its storage capacity. Exact? Lake Oroville holds exactly 3.54 million acre feet by definition? No, it's approximate. And how many sig figs? 3 sig figs. Okay, express the volume of Lake Oroville in A, cubic feet. Let's do that first. And so dimensional analysis, we just, again, just look for things that can convert from one unit to another or relate one unit to another unit. And sometimes we have composite units, and so we have a choice. And so what's given here? What's given is this. We have a fixed amount of capacity here, 3.54 times 10 to the 6 acre feet of water. That's the volume of water. And then what we got to do is we got to figure out how many cubic feet this is. And so this is my target. Now what I have to do is I have to pick a path through the jungle to figure out how I'm going to get from here to there. You know, but I don't have any kind of path in mind. I just start looking at for what works. And so for dimensional analysis, we just start writing something down. For example, we would do something like this, where we try to get rid of acre, or we try to get rid of acre feet. So we try to get rid of the whole thing or part of it, or we try to get rid of feet. And so we could either cancel out acre alone and leave feet, we can cancel out acre and feet and replace it with something else, or we can cancel out feet and replace it with something else. And so what we got to do is we got to think about, you know, what we have. So for acres, we have something, we have a relationship that was given. What is it? There's 640 acres exactly in a square mile. Do we have anything with acre feet that you have memorized or you can look up? No, so this is a dead end. We're not going to go anywhere. How about with feet? Yeah, we can go from feet to inches, feet to yard, whatever. There's lots. But do we want to get rid of feet? No, we want feet at the end, so it doesn't make sense to get rid of it. And so it looks like the only path we have is this. We can get rid of the acres and leave the feet. But now we have funny units. We have another composite unit, which is square miles foot. So if I have a square mile of land and I submerge it in a foot, that's how much water I have. You know, or how many miles, feet of water, square miles, feet of water I have. But anyway, I got rid of acres. Now what do I want to get rid of? I want to get rid of miles. Well, I know something that gets rid of miles. What is that? Yeah, there's 5,280 feet in 1 mile. But I have a problem. The problem is this is length, this is area. Do they cancel out? No. But, you know, length and area don't cancel out, but if I take length and square it, you know, then that is area. And so, you know, there's an easy fix for this because miles squared does not cancel here. I can cancel out one of them. I can cancel out this miles of one of these, but it leaves me with a mile. So I could use this 2 times in a row, or I could do this. I could just go ahead and square it. When I square the whole thing, I have to square everything inside the parentheses. That is, I have to square the 5280. I have to square the feet. I have to square the 1, and I have to square the miles. I got to square everything in there. And so when I do that, this is what it looks like. It's going to be 5280 squared feet squared per 1 squared mile squared. So if I have a square mile, how many square feet are in a square mile? And so we could just take a quick calculation here. It's going to be 5280 squared. 27 million is equal to 27,878,400 square feet in 1 square mile. And so this is the relationship I could use here. And, if I square everything, then what happens is the mile squared cancels out the mile squared and leaves us with feet squared. Well, if I have a feet squared times a foot, what does that give us? A foot squared times a foot gives us a foot cubed. And so I'm done. This is it. This is going to take me to cubic feet. Okay, so what I'll do this, I don't want to do multiple calculations. I'd rather do this all in one sequence. And so I'm not going to do this side calculation here. If I were going to punch this in the calculator, this is the way I punch it. And you can try it too to see if it works. I would do 3.54 times 10 to the, oops, that didn't work. Try that again. 3.5, how come that didn't work? 3.54 times 10 to the 6th divided by 640. Divided by 640 times, I'm going to just times it by 5280 squared. 5280 squared equals this. So how many cubic feet are in an acre foot? This many acre feet. This is what we get. Lake Oroville would have 3, 6, 9. 154,202,400,000. So at capacity, Lake Oroville would be able to contain 154,202,400,000 cubic feet of water. Are we allowed this many sig figs? How many sig figs are we allowed? 3. So I have to round this. When I round this, I could just do 154 times 10 to the 9th cubic feet. I might leave it like this. I might not convert it to 1.54, because if I convert it to 1.54, it would be 1.54 times 10 to the 11th. I might just leave it like this, because I know 10 to the 9. 10 to the 9 is what? What's 10 to the 9 called? A billion. And so there are 154 billion cubic feet of water. 154 billion cubic feet of water in Lake Oroville at capacity. This is a multi-part question. Let's look at part B. All right, any questions on this? Part B, express the volume of Lake Oroville in cubic meters. So, okay, we just did cubic feet, now we're going to do cubic meters. But I don't start from here. We already got the cubic feet. And even if this is the right path, I don't start from here because that's more subject to round-off error. Oftentimes we won't input all the digits into our calculator. Rather, I just start from the beginning. If we start from the given, then we aren't introducing any round-off error into the problem. Usually it doesn't take too much time to set everything up. So let's do part B in cubic meters. 3.54 times 10 to the 6 acre feet equals how many cubic meters? So again, you know, this is like the path through the jungle. I have no idea where I'm going. I'm just going to try different paths until I get there. And so 3.54 times 10 to the 6 acre feet. Now I have a choice. I can get rid of acres, I can get rid of feet, or I can try to get rid of both. What are you going to do? Well, we got to get rid of acres. No doubt about that. So 640 acres per square mile. And then I've got to get rid of miles, right? I think. Let's get rid of miles. 1 mile is 5,280 feet. But this is length, not area, so what do I need to do? Square it. In other words, or multiply it, 2 times in a row, and then I can cancel out the miles, right? The same thing. Now I have cubic feet. Actually, I have square feet here. Let's get rid of square feet. How can I get rid of square feet? Well, what do I know? Okay, well, I don't know square feet. I know feet, though. And so I can go from feet to what? Yards? If I go feet to yards, is that the right path, or do you think I'm starting to veer off? Starting to veer off. I could go to feet to inches. Is that the right path, or am I veering off? Feet to inches. It seems like it's the wrong path. I need to get to the metric units. So how can I get to metric unit? Should I do do you have how many centimeters are in a foot memorized? No, but you have how many centimeters in an inch memorized, because that's an exact conversion factor. So I'm thinking I need to go from feet to inches, because from inches I can easily go metric. Right? And so I do this. I need to get rid of feet squared, so to get rid of feet squared, I just square the whole thing. And so that would be 12 squared. 12 squared is 144. Inches squared, 1 squared is 1 foot squared. And so there are 144 square inches in a square foot. Right? But there's a problem, because you know what? I forgot about this foot here. And so, yes, I got rid of this foot, but there's still a foot there, and I don't want any feet in my final answer because it's meters. And so, you know what? I actually have not foot squared, I actually have feet times foot squared gives me foot cubed. And so I got to get rid of 3 of these, so I need to cube it. So what is 12 cubed? Let's take a look. $1,728. And so 12 cubed is 1728. There are 1,728 cubic inches in a 1 cubic foot. 1 cubic foot. That's a lot. Cubic inches in cubic foot. Okay, now it works out. This is the whole point of this is dimensional analysis. This is how we know we're going along the right path. We know we're going along the right path because we're stringing everything together. Everything should be canceling out. You can't just all of a sudden jump from one unit to another. Everything has to cancel out accordingly. So acres, mile squared, feet cubed, feet cubed. And that leaves me with cubic inches. And so far I know the path is correct. Well, it could dead end. We don't know. But, this I don't think is going to dead end because we need to get rid of inches. What do we know? There are 2.54 centimeters in 1 inch. And so what do I need to do here? I need to cube it. And so this gives me 2.54 cubed. 2.54 cubed is about 16 centimeters cubed in an inch cubed. So let's see what it is. I'm just going to go ahead and calculate it. 2.54 cubed, 16.387064 cubic centimeters in a cubic inch. We have to be careful here because do you know how many cubic centimeters are there in 1 milliliter? There's 1 cubic centimeter in 1 milliliter by definition. Do I have to cube this? That is, there's 1 cubic centimeter in a cubic milliliter. Does that make any sense to you? It shouldn't make any sense to you because of this. A centimeter is a unit of length. To convert it into volume, we have to cube it. A milliliter is already a unit of volume. If we cube it, it becomes totally meaningless. This is already volume. So this is volume. It matches. But over here, this is centimeters is length, inches is length. To convert these into volume, we've got to cube the whole thing. And that gives us what we call the cubic or the volume conversion factor. And then we have the area conversion factor there. And so what this does is it gets rid of inches and brings us to centimeters. Now we got to get rid of centimeters or cubic centimeters. So do you know? Well, we got cubic centimeter here. Should we go from cubic centimeter to milliliter?
No.
That would get rid of my cubic centimeters, but would that be the right path? No, that would be a dead end path. We'd pretty much not be getting any closer. And so we're going to go from centimeters to what? Meters. Yeah. And so we know that there are 100 centimeters in a meter, and then we just cube it, the whole thing. And so 100 is 10 squared, so 10 squared cubed is 1 million. And so there are 1 million cubic centimeters in 1 cubic meter. That's the way I'd read this. All right, so the centimeters cubed cancels out the centimeters cubed, leaving us with meters cubed, and then we're done. Pretty much with the setup, because the dimensions worked out. We figured out. It's a lot of conversion factors, so it's a lot of, steps in this calculation. Thank you. All right, now let's just take a quick look at the sig figs. This is how many sig figs? How many sig figs? No, this is by definition. Exactly 640 acres in square mile. If it's by definition, it's infinite. This one, by definition, it's infinite. This one, by definition, infinite. Infinite. This is a weird one because you think it's 3 sig figs, but it's by definition, it's infinite. This one, infinite. And so our final answer is allowed 3 sig figs. So let's go ahead and calculate it. It's going to be 3.54. No, I started all over. I started all the way back at the beginning, even though I was halfway along the path or something earlier, It's best just to start from the beginning like this. And so 3.44 times 10 to the 6th divided by 640 times 5280. This is 5280 squared times 12 cubed times 2.54 cubed divided by 100 cubed equals. What do we get here? $4,366,525,704.91822205. Are we going to write that many digits? No. Normally, what we do is we write, at least one more than we're allowed. And so normally, this is kind of a waste of time to write this many because we're going to drop most of them. And so we just want to write one more than we're allowed. This is cubic meters. And so the way I would have done it is 4.366 times 10 to the 9 cubic meters of water, which rounds to 4.37 times 10 to the 9 cubic meters of water. Now, take a look at this. Shouldn't I have rounded this? Look at, I wrote 4.366, but I dropped the 5. If I drop a 5, I need to round up, don't I?
Yeah, but you're running all over the place.
Yeah, but I'm going to have the domino. Remember the domino effect? Therefore, we're only allowed one rounding step. The one rounding step, I'm dropping a 6. I'm dropping this 6. I'm not really dropping the 5. I'm dropping everything. But the 6 is the drop digit. And so therefore, I round up here. All right, are we good with this? So this will be 3 sig figs. Yeah.
Yeah, at the second conversion factor, the 5,780 feet to a mile, there's a squared, right? And then does the squared cancel out with the cubic feet?
No.
So what, the feet squared stays?
No. Because you have a foot over here. And this foot times foot squared gives you a foot cube. The foot cubes cancel out.
Oh, okay.
You see?
Yeah, I see it now. So they do cancel out.
Yeah, they do cancel out. It's tricky. All right, ready to go on one on your own? Well, actually, not necessarily on your own. You could work with your neighbors in case you get stuck or your friends. But I want you to do 75C. How many gallons of water is Lake Oroville?
There's also a quiz on
Yeah. All right. Another one of these. Tell me if that is enough card. Can you work on it on the index card? So how many gallons is Lake Oroville? Gallons of water. But you're going to need some additional information. Let me put it on the board. You're going to need the volume conversion factors or volume relationships. We talked about this one, liters, milliliters to cubic centimeters is exact. This one we really didn't count. 1 liter is about 1 quart. 1 liter is about 1 quart. This is the one that most people remember. 1 gallon is 3.785412 liters. But do most people remember that? Is that an exact number? What do you think?
No.
Exact? No, this is not an exact number. Well, what most people do is they memorize it to how many sig figs, or they don't even memorize. You don't have to memorize this one. This one will typically be given. But how many sig figs would you like to use it to? In this particular problem, if we use this one, I'm not saying you have to use it, but if you use it, you should use it to 4 sig figs. At least. Well, we're given 3. If we're given 4, then you should use it to 5 sig figs. If we're given 5, then you should use it to 6 sig figs. We always want one more. It's because we have a choice. Our given, we don't have a choice. You just got to take the given as for what it is. But these conversion factors, these relationships, we have a choice. And sometimes people want to be lazy and they just want to write one. Some people say, like, a gallon's about 4 liters. Leave it at that. It's not very precise.